If you fall into a small black hole, you may be torn apart before you ever reach the point of no return. But if you fall into a giant one, something stranger can happen. You can cross the event horizon without feeling anything at all. No impact, no surface, no flash of light, no sudden stopping of time. That is the first wrong picture most people have. A black hole is not a hole with an edge you can touch. It is not a drain in space. It is a region where gravity has changed the structure of the future. Outside the black hole, escape is difficult. Inside the event horizon, escape is not difficult anymore. It has been removed from the list of possible futures. The usual phrase is that not even light can escape. That is true, but it can also be misleading. Light does not slow down at the horizon. Locally, light still moves at light speed. The problem is not that light becomes too weak. The problem is that every path light can take now leads deeper inward. The future has tipped. That is what makes a black hole different from any ordinary dangerous object. A planet has gravity. A star has stronger gravity. A neutron star has gravity so intense that matter is crushed into extreme density. But if you are outside those objects, escape remains physically possible. You may need enormous speed. You may need impossible engineering. But the direction called away still exists. Inside a black hole, away is no longer a future-directed direction. To make a black hole, mass must be compressed inside a critical radius. For the Sun, that radius would be about 3 kilometers. If the Sun's entire mass were squeezed into a sphere only a few kilometers wide, the region around it would become a black hole. For Earth, the critical size is roughly that of a small marble. Earth is not close to becoming a black hole, because its mass is spread across thousands of kilometers. The point is not that black holes require magical matter. The point is compression. Enough mass, inside a small enough region, bends space-time so severely that escape stops being part of the geometry. This is why the event horizon is not a wall. It is a boundary in cause and effect. From outside, it marks the last place from which light can still reach the distant universe. From inside, it marks the moment when all future paths lead inward. If you watched someone fall toward a black hole from far away, you would never see the fall the way they experience it. Their clock would appear to slow. Their light would stretch toward redder wavelengths. Their image would become dimmer, weaker, more delayed. In the idealized picture, they seem to freeze near the horizon and fade away. But from their own point of view, time does not freeze. Their watch keeps ticking, their thoughts continue. Their heartbeat does not pause because a distant observer sees their light arriving more slowly. This is one of the hardest parts of relativity to accept. There is no single universal clock sitting outside reality. Time is measured along a path through space-time. For the falling person, the horizon is crossed after a finite amount of their own time. The black hole separates descriptions. The outside observer sees fading and delay. The falling observer experiences crossing and continuation. Both descriptions are part of the same geometry. What happens next depends on the size of the black hole. Near a small black hole, the danger begins before the horizon. Gravity is not the only issue. The real killer is the difference in gravity from one part of your body to another. If you fall feet first, your feet are closer to the black hole than your head. They are pulled into a slightly different path. Near Earth, that difference is tiny. Near a small black hole, it can become enormous. This difference is called tidal force. Tidal force stretches you along the falling direction and squeezes you from the sides. It is not a single clean pull. It is a gradient. Your body becomes a measuring instrument for the curvature of space-time. Your feet and your head are being assigned different futures. Bones, blood vessels, nerves, organs, and cells are all held together by ordinary physical forces. Those forces have limits. Near a small black hole, space-time can demand more than those structures can survive. This is the process often called spaghettification. The word sounds almost comic. The reality is not. It means the body is stretched because gravity changes too sharply over its length. You are not being cut by a blade. You are being separated by geometry. For a stellar mass black hole, perhaps a few times the mass of the Sun, the tidal forces near the horizon can be so severe that a human body would be destroyed before crossing. In that case, the event horizon is not the first thing you experience. You never get a clean moment of passage. The black hole tears the body apart outside the boundary. But a supermassive black hole is different. This is the part that sounds wrong at first. A larger black hole can be gentler at the horizon than a smaller one, not because it is weak, not because it is safe, but because its horizon is enormous. The change in gravity across the length of your body can be much smaller at the horizon of a supermassive black hole. If the black hole has millions or billions of times the Sun's mass, you could cross the event horizon without being immediately torn apart. There would be no local sign that the most important boundary had just been crossed. This follows from Einstein's equivalence principle. In a small, freely falling region, gravity can disappear from your local experience. An astronaut orbiting Earth feels weightless, not because Earth's gravity is gone, but because the astronaut, the spacecraft, and everything inside are falling together. Near the horizon of a very large black hole, the same idea applies. If you are falling freely, your immediate surroundings may feel ordinary, but ordinary does not mean safe. The event horizon is not detected by local touch. It is defined by the global future of light. You could shine a flashlight outward after crossing the horizon. Locally, the light would move away from you. Nothing strange happens to the beam in your immediate frame, but the beam's future still points inward. It cannot reach the outside universe. That is the trap. A useful way to picture this is with light cones. A light cone represents all the directions a signal can move from one event without exceeding light speed. Far from the black hole, your future light cone includes outward paths. You can move left, right, inward, outward, or send signals in many directions. Near the horizon, the cone begins to tilt. At the horizon, the outward edge just fails to escape. Inside, the entire future cone points inward. This is why no rocket can save you after crossing. A rocket can change your motion within your future light cone. It cannot move you outside causality. To escape from inside the horizon, you would need a path that leads outward to the distant universe. General relativity says that path is no longer available. You are not trapped because your engine is too small. You are trapped because the future has only one direction left. If you could remain alive after crossing a supermassive horizon, the outside universe might still be visible for a while. Light from stars, gas, and distant space could still fall in after you, but the view would be distorted. A black hole bends the paths of photons. Light from behind it can curve around it. Stars may appear, shifted, duplicated, or compressed into strange rings and arcs. The sky would no longer behave like the sky your brain expects. Yet the visual distortion is not the deepest part. The deeper change is causal. The outside universe can still send light into your region, but you cannot send a message back. The horizon has made communication one way. After that, the remaining time depends on the black hole. In a small black hole, the time between horizon and destruction can be extremely short. In a supermassive black hole, it can be longer. But inside a simple, non-rotating black hole, the central singularity lies in your future. It is not simply a place you can steer around, it behaves more like an unavoidable moment. That sentence is strange because our instincts are built for ordinary space. In daily life, a dangerous place can be avoided by choosing another direction. You can go left instead of right. You can turn back. You can stop. Inside a black hole, the situation is different. The inward direction is woven into time. Every future-directed path leads toward smaller radius. The singularity is often described as an infinitely dense point at the center. That is the common phrase, but it needs caution. In classical general relativity, the singularity is where the mathematics breaks down. Curvature becomes infinite. Quantities that should remain physically meaningful stop behaving. This does not necessarily mean nature contains a literal point of infinite density. It means the theory has reached a place where it can no longer give a complete answer. Most physicists expect that a full theory of quantum gravity would be needed to describe the deepest interior. That theory is not complete. So the honest statement is this. General relativity predicts that all inward paths end at a singular boundary of the theory, but the final microscopic reality is unknown. That uncertainty does not make the black hole safe. Long before the final unknown, tidal forces would grow. Even in a supermassive black hole, where the horizon may be gentle, the curvature increases as you move inward. The difference in gravitational pull across your body becomes larger. Stretching increases, compression increases. Eventually, the body can no longer remain a body. At first, the effect may be too weak to notice. Then it becomes mechanical stress, then injury, then disassembly. The body is not destroyed because it hits something solid. It is destroyed because space-time no longer permits all parts of it to continue together. Cells depend on molecular bonds. Organs depend on tissue structure. Consciousness depends on a functioning brain. A person is not just matter. A person is matter arranged in an extremely delicate pattern. Near the interior of a black hole, that pattern cannot remain intact. The forces that hold the arrangement together are overwhelmed by the geometry assigning different paths to neighboring parts. This is death by curvature. There is another question hidden behind the fall. If you carry information into a black hole, the arrangement of your atoms, the state of your brain, the pattern of your body, is that information destroyed? Classical general relativity seems to hide it behind the horizon. Quantum mechanics suggests information should not simply vanish from the universe's bookkeeping. This tension is the black hole information problem. Stephen Hawking showed that black holes should emit a tiny amount of radiation because of quantum effects near the horizon. For large astrophysical black holes, this radiation is unbelievably weak, far too weak to matter for a falling person. But conceptually, it is one of the deepest problems in physics. If a black hole slowly evaporates, what happens to the information about everything that fell in? This question remains debated in its full form. Some modern ideas suggest that information is encoded in subtle ways at the horizon or in correlations within the radiation. The established lesson is that black holes connect gravity, thermodynamics, quantum theory, and information in a way no ordinary object does. But this does not mean the falling person survives. Physical information is not the same as personal continuity. A pattern may be encoded in the universe's accounting without preserving a living mind, a body, or a self. Physics can ask whether information is erased. It cannot turn that into a promise of survival. So what actually happens when you fall into a black hole? From far away, you slow, redden, dim, and disappear. From your own point of view, you continue forward. If the black hole is small, tidal forces destroy you before the horizon. If it is enormous, you may cross the event horizon without noticing the exact moment. After that, the outside universe is no longer reachable. Every possible future points inward. Eventually, tidal forces tear apart the structure that made you a body. Classical physics then carries what remains toward a place where the theory itself fails. The most disturbing part is not that a black hole is violent. Sometimes it is. The most disturbing part is that the point of no return may be quiet. No wall, no warning, no surface. Just a boundary you pass without feeling it. And after that, escape is not hard. Escape is no longer real.